Hello there and welcome back to Magnetism. In this video we're going to be looking at induced potential transformers in the national grid, and this is video number 3 of 3 for our magnetism and electromagnetism topic. Next, I recommend that you do the end of chapter test, or alternatively you can look at the first space physics video. Firstly, we're going to have a look at something called induced potential. If an electrical conductor moves relative to a magnetic field, or if there is a change in the magnetic field around a conductor, a potential difference is induced across the ends of the conductor. If the conductor is part of a complete circuit, a current is induced in the conductor, and this is known as the generator effect. So in some ways, the generator effect is the exact opposite of the motor effect. The motor effect uses magnetism to change electrical energy into kinetic energy, and the generator effect uses magnetism to change kinetic energy into electrical energy. Let's have a look at how the generator effect works. If we take a wire and cut across field lines, then there will be a potential difference induced in the wire. If the direction is changed, then the potential difference goes the other way. If we do this with a full circuit of wire, then we get a current which flows. The greater the magnetic field strength, the greater the induced potential or induced current. The greater the speed of the moving wire, the greater the induced potential. And the greater the amount of wire cutting through the field lines, the greater the induced potential. If the wire is coiled, as seen in the last slide, the more coils, the more the induced current / induced potential. So these are the three factors which affect the size of the induced potential: the magnetic field strength, the speed of the moving conductor, and the amount of wire which cuts through the field lines. If we reverse the poles of the magnetic field, then we will reverse the direction of the potential. If we reverse the direction in which the conductor or wire is travelling, then we will also reverse the direction of the induced potential. So these are the two factors which affect direction of the induced potential. But it is more complicated than that. Can you remember back in the section on the motor effect, we learned that a wire carrying current generates a magnetic field. So this was the right-hand rule. If you have some sort of wire carrying a current, then a magnetic field will be induced around that wire. The wire which is having a potential induced carries a current, and this current will then produce its own magnetic field. But the problem is, this magnetic field acts in the opposite direction of the field which is being used to generate the electric current. So if you remember back to electromagnetism, we looked at a current carrying wire and the magnetic field. Remember, just the right-hand rule stuff, the magnetic field which became a thing because of that current carrying wire. Now, if you have a current carrying wire moving through a magnetic field, you get the motor effect, remember. But when you have the generator effect, what you're doing is you're making a current go through that wire. But then the magnetic field which comes out of that wire then acts to oppose the original change. This means that the magnetic field induced by the current carrying wire will act to oppose the change in the generation of potential difference. So this means work has to be done to overcome this force acting in the opposite direction. When a wire is moved through a magnetic field, it will experience a force which acts against the original change. Therefore, it requires work to be done to change the kinetic energy into electrical energy. So what this essentially means is you can't get any energy for free. In order to get electrical energy induced in a wire, you have to actually put force in to move the wire. You can't just get it for free. We know that energy can't be created, it has to come from somewhere. So when we use multiple coils or a larger external magnetic field, yes, it will produce a greater electric current, but it will also require more energy input. the kinetic energy of the wire moving must also be greater. So if you have one coil of wire and you cut it through field lines, you will have to put in some force to keep it going, right? But if you have 5 coils, you're going to have to put 5 times the amount of energy in, or 5 times the force, to actually move that wire through the field, because you can't just get more electrical energy for free. You have to get that energy from somewhere. If you're following along in your Magnetism and Electromagnetism workbook, pause the video now and complete task number 6. Next, we're going to have a look at uses of the generator effect. We have seen that the generator effect produces a potential difference and therefore a current in a wire moving in a magnetic field. We can design machines to take advantage of this and produce alternating and direct current. A device which produces alternating current is called an alternator, and a device which produces direct current is called a dynamo. Now, just a quick note, I understand this is very, very difficult. I would argue that this is perhaps the most difficult part of the whole GCSE. Magnetism and electromagnetism is a very tough topic, and I feel like this part, and the part that we've just covered there, is really tough. So don't worry if you find it difficult. This is one of those things where practice makes perfect. You might need to look over this a few times, do a lot of practice questions, and it will come to you. But I understand this is difficult stuff, so we'll try and go through it slowly, and I'll try and explain everything that I can. Okay, the first thing we're going to look at is an alternator. When the coils rotate through the magnetic field, the current produced travels through the wires. Now, we can see that there's a north pole here and a south pole here, and we've got these coils of wires here, alright? Now, this part of the coil is attached to this ring here, and this part of the coil is attached to this ring. So when it rotates, this part of the coil is always touching wire B, and this part of the coil is always touching wire A. When one side of the coil moves upwards and the other moves downwards, we will get a negative current being produced. And this is then transferred to both of the outgoing wires. Alright? So when one moves up and one moves down, we're going to have a negative potential. Then, once the other side moves upwards and the alternative side moves downwards, we will get a positive current being produced. This current will again be passed on to both of the outgoing wires, because remember, this part of the coil here is always touching wire B, and this part of the coil here is always touching wire A. So that means both of the wires are going to get a constant alternating current, because you get part of the current in the positive and part of the current in the negative. So both wires are going to get an alternating current. And this is what the current looks like on a graph. An alternator produces a current which looks like this: regions of positive and regions of negative. Now remember, we only get induction when the coil's wires cut through field lines. So when the wires are at the part of the cycle where they travel parallel to the field lines, we'll get no induction. So let's just go back and see what I mean. So when this part of the coil is going this way in the field, you're not actually going to get any induction at all, because it's not cutting through field lines, okay? But when the coils pass right through, they pass 90 degrees to the field lines, that's when you get the maximum potential being induced. So at the peak here, this is where the coil is going right through the field lines, but here, this is where the coil's travelling parallel to the field lines, and you actually get no potential being induced at all. Now, I know that's quite difficult to look at and understand from a static diagram, so here's an animation to show exactly what I mean, okay? So you can see here that this part of the coil on the right is attached to this coil here, this ring here, sorry. Now the left-hand part of this coil is attached to this ring here. So what you find that this part of the coil always connects to the negative end, and this part of the coil always connects to the positive end. So what you get is you get an alternating current, because this part is going upwards here, but then it's going downwards here, you see that? So the same part of the coil, which is connected to the same wire, both goes up and down through the field. Now if it goes both up and down, well remember, when you change the direction which the wire travels, you change the direction of the induced voltage. And that means you get a graph which looks like this, both positive and negative. And the only reason you get that is because the same part of the coil is connected at all times. So it goes both up and down, which means you get an alternating current. Okay, next we're going to have a look at the dynamo. The dynamo works with a similar principle, except we use a split ring commutator rather than rings connected to each wire. Now this ensures that the part of the coil travelling upwards is always connected to the same wire, and the part which is travelling downwards is always connected to the other. So here we'll have the outgoing wires and we've got a split ring commutator. As this coil moves around, what you're going to find is you're going to find that this side here is at the minute connected to the right hand side. But once it does a full revolution, this part here will then be connected to the left hand side. So in other words, the part of the coil which is going upwards will always be connected to this wire here, and the part of the coil which is going downwards will always be connected to this wire. So that means because the one wire is always connected to the part which is going upwards, you're going to get a current which is direct. You're not going to get an alternating current anymore. You're going to get a direct current. The dynamo produces direct current, or current which does not fluctuate between positive and negative. That is because each wire is always connected to the same part of the coil, whether that be up or down. Direct current from a dynamo is periodic, like an alternator. However, it is always the same charge. It's always positive or negative. When the coil wires move parallel to the field lines, we get no current produced. So again, when these parts of the coil go right through and intersect with the field lines, you get a peak in the current. But when they travel parallel to the magnetic field lines, you get no current. But notice this time, it's always the same polarity. It's always positive, never negative. Or alternatively, it could always be negative and never positive. But we don't get an alternating current, we get a direct current. And this shows how a dynamo works. So when this spins around here, you can see this is actually a very bad animation, but you see this here is a split ring commutator. So you see that this part of the coil is always connected. The part which is going down is always connected to this wire here, and the part which is going up is always connected to this wire here. So you don't get one wire and part of the coil going up and down. You get one part of the wire where the coil is always going up or always going down, and that means you get direct current like this rather than alternating current. So a dynamo uses a split ring commutator and an alternator uses rings. If you're following along in your Magnetism and Electromagnetism workbook, pause the video now and complete task number 7. Right, last little bit now. We've got microphones and we have transformers to do, and then that's Magnetism and Electromagnetism finished. Thank goodness. Now remember, when a conducting wire is passed through a magnetic field and it cuts through field lines, a potential difference is induced in the wire. The induced potential difference creates a current in the wire, and we know that from a long time ago now. We're going to have a look at a moving coil microphone. You can see that this setup of this looks quite similar to the loudspeaker. Both involve a coil wrapped around something and being found within a magnetic field. So this does look quite similar to a loudspeaker. The only difference is a loudspeaker has a very slightly different shape. And the principle is basically the exact opposite of a loudspeaker, because a loudspeaker uses the motor effect to produce sound, whereas a microphone uses the generator effect to turn sound into an electric current. You can think of a microphone, oh look, this is just what I was saying. You can think of a microphone as the opposite of a loudspeaker. A loudspeaker uses the motor effect to convert electrical current into kinetic energy and subsequently sound energy, and the microphone does the exact opposite. So again, this is like a cut-through diagram of a microphone, a cross-section. This is what you would see if you went right through a microphone like that. So this part of the microphone here has coils wrapped around like that, and that's what these orange circles are. That's like part of the coil. And then this is a magnet here, so these coils are moving up and down inside of a magnetic field. A microphone uses the generator effect to convert kinetic energy into electrical energy. When someone talks or a sound is made, the sound waves interact with the microphone to make it vibrate backwards and forwards, or in this case, up and down. So the microphone is travelling upwards and downwards in the diagram above as the sound wave interacts with it. Compressions and rarefactions in the wave make the microphone go up and down. As there is a conductor passing through a magnetic field, a current is induced, and its frequency matches the frequency of the sound wave. So the electrical current represents the sound wave in the form of a signal, and that might go off to some sort of computer to be recorded. Okay, we're now going to have a look at something completely different. We're going to have a look at transformers. Transformers are pieces of equipment which can step up and step down the voltage of electricity. You can see them on power lines around the country, and that's what they look like. They look like these big boxes on power lines that you sometimes find. Now, transformers are very useful, as it is better to transport electricity over longer distance at higher voltages to reduce losses. So if you were to produce electricity at a power station, for example, you might produce it at X voltage, and you want to transport it all the way across the country. If you transport electricity at too low a voltage and too high a current, what you find that the wires will actually heat up, and that's wasted energy, that's thermal energy. Now, we don't want wasted energy, we want to reduce the losses. So in order to reduce the losses, you bump up the voltage and reduce the current, okay? So it's the same power output, but it's much more efficient because you're reducing the amount of energy which is being wasted in thermal energy when it's being transported through transmission lines. They work with two principles which we have learnt about in the course of this topic: electromagnetism and induction. Now, this is the structure of a transformer. Wires wrap around the iron core of the transformer. Iron is used because it is very easily magnetised, just like an electromagnet. So here we've got a solenoid with an iron core. So we'll have an electromagnet. If we have a current coming in to this transformer here, we will get a magnetic field induced in this iron core. All right, and what we'll find that the magnetic field will be travelling in a certain direction. Let's say it's going up on this side, for example. It'll be going up through here, around here, and then down through this solenoid. Now, if we have a changing magnetic field inside of a coil like this, then you will get the generator effect. Now, the thing about transformers is transformers only work with alternating current because you have to have a change in magnetic field in order to produce an electric current or a potential difference. So in order to get any sort of electricity out of a transformer, you have to have a change in magnetic field in this part of the transformer. And in order to get a change in magnetic field, you have to have a change in current on this side of the transformer. When an AC electrical current is passed through the wire on the left, a magnetic field is produced in the iron core. This is very similar to an electromagnet. This magnetic field then passes through the transformer's iron core right around the whole loop. The wires which pass over the iron core on the other side are crossing magnetic field lines, and so a potential difference is induced in the right-hand wire. Now, we'll have names for the different parts of the transformer. This part of the transformer is called the primary coil. This part of the transformer is called the secondary coil. And you do need to know that for the exam. The ratio of the potential differences across the primary and secondary coils of a transformer depend on the ratio of the number of turns on each coil. So if we double the amount of coil turns in the secondary coil, then our voltage will double across our transformer. If we have a transformer which takes in voltage and increases it, we call it a step-up transformer. Transformers which decrease voltage are known as step-down transformers. And there's a formula which you need to understand how to use. It is given to you in the exam, this one, but you need to know how to use it. And this is the formula. The voltage across the primary coil divided by the voltage across the secondary coil is equal to the number of primary coil turns divided by the number of secondary coil turns. So the next equation which you need to know is shown here. This equation appears on the physics equation sheet, so you may not need to know it, but you will need to know how to use and rearrange it. And it is a bit of a tricky one, this one, because you don't just have a value on one side of the equation. Both sides of the equation involve this fraction. So let's do a worked example. A step-up transformer has 8 turns on its primary coil. If a voltage of 7 volts is applied across the primary coil, and the secondary coil has 20 turns, what is the voltage across the secondary coil? Okay, so the first thing we're going to do is write out our formula. The voltage across the primary over the voltage across the secondary is equal to the number of turns in the primary over the number of turns in the secondary, okay? Okay, so we're going to sub in with values. So that leaves 8 over 20 is equal to 7 over the voltage of the secondary coil. Well, 8 over 20 is equal to 0.4, so 7 over Vs is equal to 0.4. If we take this equation here and we divide both sides by if we rearrange it to get the 7 on this side, then Vs is therefore equal to 7 over 0.4. 7 over 0.4 is just 17.5. So the voltage is measured in volts, so our final answer is 17.5 volts. Let's have a look at another worked example. A step-down transformer has 5 turns in its primary coil. If a voltage of 15.8 volts is applied across the primary coil, and the secondary coil has a voltage of 3 volts, how many turns does the secondary coil have? Right, so again, first thing we're going to do is write out our formula. Voltage across the primary over voltage across the secondary is equal to number of turns in the primary over number of turns in the secondary. Subbing in our numbers, we'll have 15.8 divided by 3 is equal to 5 over the number of turns in the secondary coil. Well, 15.8 divided by 3 is 5.27. So now we'll have that 5 divided by the number of turns in the secondary coil is equal to 5.27. That means we can rearrange it to get 5 divided by 5.27 is equal to the number of turns in the secondary. 5 divided by 5.27 is 0.948. Now, the number of turns is unitless, it's just a number. So our final answer is 0.948 turns. And that just means you'll have very slightly less than 1 turn in the coil. Now, that's not all for transformers though. There is another formula that you need to know as well. This formula is incredibly useful when it comes to working out how many turns a coil needs to get a desired voltage. But you also need to know the conservation of power equation. Remember from the electricity topic we learned that power is equal to current times voltage, or P is equal to IV. Well, this applies to transformers as well. If a transformer is 100% efficient, then we know that the input power is equal to the output power. Or in other words, power primary is equal to power secondary. And as we know, power is equal to current times voltage. So if we just replace the left-hand side here of the equation, power primary, well, we can just write that as voltage primary times current primary. Alright, so all we're doing here is changing the left-hand side of the equation from the power to voltage times current, because power is equal to voltage times current. Now, for this side, we're going to do exactly the same. Secondary power, well, that's just equal to the secondary voltage times the secondary current, okay? And this is the equation for conservation of power, and that's what we're going to be working with next. Voltage primary times current primary is equal to voltage secondary times current secondary. And this is the next formula that you need to know. Let's have a look at a worked example. A transformer is 100% efficient. So, if it's 100% efficient, we can use the conservation of power equation. If a voltage of 10 volts is present across the primary coil and a current of 7 amps is flowing, and the secondary coil has a potential difference across it which is 6 volts, what is the current flowing through the secondary coil? Alright, so again we're going to write out our equation. Voltage in the primary times current in the primary is equal to voltage in the secondary times the current in the secondary. Well, subbing my numbers, we'll have 10 times 7 is equal to 6 times IS. Well, 10 times 7 is 70. Now, if we divide both sides of this equation by 6, we'll get 70 divided by 6 is equal to the current in the secondary. Current in secondary is 11.66. Since current is measured in amperes, our final answer is 11.66 amps. Now, this is what the course specification says you need to know. Students should be able to explain how the effect of an alternating current in one coil in inducing a current in another is used in transformers. Explain how the ratio of the potential differences across the two coils depends on the ratio of the number of turns on each. Calculate the current drawn from the input supply to provide a particular power output, and apply the equation linking the potential difference in number of turns in the two coils of a transformer to the currents and the power transfer involved, and relate these to the advantages of power transmission at high potential differences. So let's just check we can do all of these things. So, can you explain how the effect of an alternating current in one coil in inducing a current in another is used in transformers? Yes, we can. The alternating current produces a changing magnetic field in the primary coil, which then produces an alternating current as there is a change in magnetic field within a coil of wire. So this is just looking back at the transformer and how it works. We know that a change in electric current leads to a magnetic field being produced. That change in magnetic field then makes a change in that change in magnetic field then makes an alternating current on the right coil, on the secondary coil. Explain how the ratio of the potential differences across the two coils depends on the ratio of the numbers of turns on each. Well, if we have a step-up transformer, then there will be a larger amount of coils on the secondary side than the primary side. If there was double, then the voltage would double. If there were triple, for example, the voltage would triple. So if the ratio between the first and second number of turns is 1 to 4, then we know that the voltage is going to quadruple. All right? The ratio between the amount of turns on the primary and secondary part of the transformer is equal to the ratio of voltages of both, okay? Calculate the current drawn from the input supply to provide a particular power output. Well, that's just the power equation, right? Take the power on the secondary coil, say 7 watts, and use the power equation to work out the current. Let's say there was a voltage across the primary coil of 3.5 volts. Then the current drawn would be P equals IV. We know power is 7 watts, so we need to divide both sides by 3.5. 7 divided by 3.5 is 2 amps. So that's just the power equation. And we need to apply the equation linking the potential difference, a number of turns in the two coils of a transformer, to the currents and the power transfer involved, and relate these to the advantages of power transmission at high potential differences. Now, we've done 2 work examples on this formula. It is slightly tricky, so practice makes perfect with this one, alright? And as I say, this part of the magnetism and electromagnetism topic is tough, I understand that. If it takes multiple watches of this video, if it takes watching videos on other channels, if it takes practice with exam questions or whatever, so be it. This is probably the most difficult part of the course, and I know lots of students struggle with it, so don't worry about it, okay? Just try and get through as many questions as you can. It will come with practice. Yeah. And talking about practice, if you're following along in the revision workbook, now it's time to do task number 8. And once you've done that, you've finished. Congratulations. Magnetism and electromagnetism revision, all done. I recommend now that you take the test and say how much you've learned so far on the course, and I wish you the very best of luck with that. Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.